Hi, this video is about estimating the camera matrix and distortion coefficients of your camera system. In the last video, we derived the camera matrix starting from the pinhole camera model, and today we'll look at the practical aspects of calibrating our system, and we'll use OpenCV to do that. So this video is all about calibration targets, how to take good pictures for the calibration, how many pictures to take, and about how to check if a calibration is accurate. So these are the parameters we want to find. There are the intrinsic camera parameters, the focal length and the principal point, and there are distortion coefficients that model the radial and optionally tangential distortion of your lens. If you're unsure about what these parameters mean, then please check out the last video. So the overall process works like this. First, you need to obtain some calibration targets. The easiest way to do so is to get them from the OpenCV website and to print them. Alternatively, you may have access to specialized, high quality, but also more expensive targets. Those are a bit harder to get. OpenCV supports different types of calibration targets. For example, the chessboard pattern, patterns with circles, and Cherukuri patterns. And we'll talk about some benefits and drawbacks of those different patterns over the course of this video. If you decide to print your target, then you can either download some pre-created targets directly or use this Python script to generate them. If you use the script, then you can tailor the size of the targets, the number of rows and columns, and some other parameters to your specific needs. But the default targets are certainly sufficient at the beginning. Then we take photos of these targets. How you take those photos is absolutely critical to getting an accurate calibration. There are a few things to keep in mind. The first has to do with radial distortion. Radial distortion is usually negligible in the center of the image and it becomes larger towards the corners, and in the very corners it can be very large. So to get an accurate estimate of your distortion parameters, it's essential to have lots of target points in the corners of your images. And make sure you get them in all corners of the image. You probably have to turn your camera sideways or upside down for that. Let me expand a bit on this point. As I said, radial distortion is usually small towards the center and large towards the edges and corners of your image. The point of the distortion correction is to reduce the distortion at the edges and corners. So ideally, after the correction, distortion is zero everywhere. It won't be zero, because we're using a model which is just an approximation of the distortion of real lenses. So there will still be an error. But that error should be as small as possible over the entire image. And we'll talk about the algorithm that's used to minimize that error in a little bit, but in general, algorithms like that one minimize an average error. So if, for example, we take pictures like these, where the target is almost always in the center of the image, but hardly ever in the corners, then the image points that the algorithm will use in the optimization will look like this. So the algorithm will make sure that the distortion over these points is minimized. But these points already suffer from little distortion. Distortion is large towards the edges and corners of the image, not in the center where these points are. If we provide a few pictures where the target is in the corner, then the result will already be a lot better, because then the algorithm has some information about the larger errors in the corners, and it will account for that in the optimization. But as I said, algorithms usually minimize an average error. So if there are many more points in the center of the image than at the corners, then the center will still have a much larger impact on the resulting distortion correction. So ideally, we should provide the algorithm with as many points as possible in those parts of the image where the distortion is large. For example, these are images where the target is always in the edges and corners of the image, and the corresponding points on the image look like that. We still have a large number of points in the image center, so there's no risk of introducing large errors there, but we also have many more points in the areas where distortion is large. So those areas will have a larger impact during the optimization, and the distortion correction that we get from this dataset should result in a more uniform error across the image. We'll look at an example of that later. Another important point is that we need to take photos at a range of different angles. So if the target is lying on the floor, don't just take images from the top down. If all your images are like that, then you won't get an accurate estimate of the focal length. We need photos at multiple angles. Keep in mind that the angles mustn't be too extreme, because OpenCV still needs to be able to find the target patterns on your images. If the angle is too extreme, then the pattern may be too distorted for OpenCV to recognize it. I found the chessboard patterns to be recognized well, even at very extreme angles, but patterns with circles seem to require less extreme angles. The next point has to do with focus breathing. Unless you've got a special kind of lens, your lens will suffer from focus breathing. So as you change the focus distance, the effective focal length of your lens will also change, which would mess with your calibration. So if you want an accurate calibration of your system, then you need to choose the focus distance at which you're planning to use the lens, and then take all calibration pictures at that focus distance. If you want to use the lens at multiple focus distances, then you'll have to do multiple calibrations. The last point is probably quite obvious. Make sure that the target on your images is in focus. The chessboard-based patterns are very susceptible to out-of-focus images. For those patterns, we need to find the pixel where adjacent squares meet. If that part of the image is out of focus, then we can't determine the location accurately. The circle-based patterns are more resilient to a little bit of blurriness, because there, the whole area of the circle is used to estimate its center. A little bit of blurriness doesn't affect the accuracy of the center as much. Okay, before we continue, let's briefly talk about how the calibration algorithms work, because we need that to be able to interpret the output of the calibration. I promise that this is the only little bit of theory that I'll talk about in this video. So the principle behind the algorithms is very simple. All of those calibration targets contain certain points that are easy to identify by our computer. In the chessboard patterns, the corners between black and white squares are easy to find, and in the circle patterns, the centers of the circles are easy to find. If we know the pattern, then we know the coordinates of these points on the pattern. For example, on this chessboard pattern, we set the coordinates of the first point to 0, 0, 0, so we choose that point as the origin of our coordinate system. And since we know the side length of the squares, we can write down the coordinates of the other points. In this case, the side length of my squares was 20 millimeters. However, for the purpose of this calibration, the absolute distances don't actually matter. So we could also just use these coordinates. Those are the world coordinates, so they live in 3 dimensions. But it is assumed that the patterns lie on the xy plane, so the z coordinate is 0. And we can do that even if the target is not on the floor. It's just how we define the coordinate system. So these are the world coordinates of our target. If we take a picture of the target, then we can find these same points on the image. So we know the corresponding image coordinates of the target. And those 2 sets of points are the inputs to the optimization algorithm. The algorithm then assumes certain initial values of the camera intrinsics, distortion coefficients, and of the poses of our cameras. And it uses them to project the known world coordinates of the target to an estimate of the image coordinates. Initially, the estimated image coordinates will not be very close to the actual image coordinates. The distance between them is called the reprojection error. The algorithm then iteratively changes the value of the camera intrinsics, the distortion coefficients, and the camera poses until the estimated image coordinates are as close as possible to the measured image coordinates. So until the reprojection error has been minimized. Okay, let's continue with the practical side. Once you've got good pictures, you need to load them into OpenCV, which you can do with this command. Then we have to find the pattern of the target on the image. How you do that depends on the pattern that you've chosen. For the chessboard pattern, it's simply done with these commands. Chessboard corners are usually recognized very well, even if you have relatively small squares. For circles, you have to use this command. Circles aren't always recognized immediately. OpenCV uses a blob detector to find patches that look like circles. If your circles aren't recognized, then you'll have to adjust the settings of the blob detector. For example, on a high resolution image, I had to increase the area of the circle that OpenCV looks for. You can visualize the circles that OpenCV has found with this command. If not all circles are found, or if other structures that are not circles are also found, then you'll have to continue adjusting the parameters of the blob detector. Finally, you can find the Jaruko pattern with these commands. The dictionary refers to the Aruko markers that are shown in the white squares of the chessboard. If you use a different dictionary, then different markers will be used. So this is very useful if you want to use multiple targets in one photo. You can't, for example, use multiple regular chessboard targets in the same image. So, after we've successfully run these commands, we've either found the corners of a chessboard or the centers of circles. And after we've done that on many images, we can use all of those points to calibrate our camera. So we use them to minimize the reprojection error that we talked about earlier. In OpenCV, this can be done with a function called Calibrate Camera. But unless you've got a high quality calibration target, this function will not give you very good results, because it assumes that we know the location of the target points exactly. But if you print your calibration target on a piece of paper, your printer won't be perfectly accurate. If you put the printed target on a surface that's not perfectly flat, then the paper also won't be perfectly flat. And if you don't use the printed target immediately, then the paper will absorb some moisture from the air, and it will start to curl or buckle, and its edges will start to lift up. So in a real-world scenario, we don't know the exact coordinates of the points on printed targets. So if we use the standard calibrate camera function, which assumes known coordinates, then our calibration won't be accurate. Instead of calibrate camera, we can use a different calibration function that's available in OpenCV. This one is called Calibrate Camera RO. The RO stands for Release Object, which is how the authors of the method describe what the algorithm is doing. In essence, rather than assuming that we know the positions of the target points exactly, we allow for some uncertainty in the coordinates of those points. And the optimization algorithm optimizes both the camera parameters, distortion coefficients, and camera poses, and the locations of the target points. We still have to provide coordinates of the target as a starting point for the algorithm, but they will be adjusted during the optimization process. The way in which the algorithm works is that it partially fixes 3 of the coordinates of the pattern on the target. OpenCV automatically chooses the first and last points of the pattern. We have to specify the third point, and OpenCV recommends to use a corner point of the pattern. So using this calibration method instead of the default one will give us more accurate results. But since this method also has more degrees of freedom, there are more parameters that we need to find, the optimization takes longer, and we also need more pictures to get a consistent result. Also, you mustn't move or touch the calibration target during the whole process. The position of all the points on the target must stay the same throughout. Okay, let's assume that we've taken good pictures for the calibration, and let's run the code that we've been talking about. The output of the calibration function gives us this information. First, it shows us the reprojection error on the images that it used for the calibration. This is given in pixels. This value should be as small as possible, less than 1 pixel. If it's larger, then there's some issue with your photos or with the pattern recognition. We also get estimates of the principal point and of the focal length. Those are also expressed in pixels. If you want them in millimeters, then you can use the formulas we derived last time to convert them. For example, here I converted the focal lengths to millimeters. You notice that in the plot that shows the focal lengths in pixels, the values of the x and y directions is almost identical, whereas in the plot in millimeters they are quite different. That's just because the sensor size in millimeters that's provided by the manufacturer is usually rounded to 1 or 2 digits. So the values in millimeters won't be very accurate. We'll just focus on the values expressed in pixels. We also get an estimate of our distortion coefficients. And you can see here that in this case I've only optimized for 3 of those parameters, K1, K2 and K3. I didn't optimize any of the higher order coefficients of radial distortion, and I didn't optimize for tangential distortion. In general, it's a good rule of thumb to start with fewer coefficients and to only add additional coefficients if you don't get a good result. And that's because some of those coefficients may not be necessary to accurately describe the distortion of your specific lens. But if you add them anyway, then you introduce unnecessary additional degrees of freedom, which can make it harder for the algorithm to converge to a good solution. Okay, so we've got these estimates and they seem reasonable. But how can we tell if they are accurate and reliable? The first thing to consider is that this reprojection error is calculated on the same images as were used for the calibration. A low value here doesn't guarantee that this output will also give a good result for other images. It doesn't tell us how well those results will generalize. An easy way of getting a first estimate of the accuracy of our calibration is to capture another set of images and to use the parameters that we found here to compute the reprojection error on those other images. In the plot, I call that validation error. And in this case, the validation error is a little higher, but still very good. Now we can think about how many pictures we need to get a reliable result. For example, what happens if we take fewer pictures? So let's also do the calibration with fewer images. Let's look at the reprojection error. As we add more images, the reprojection error increases. That could almost make you think that you should use fewer images. But of course that's not true, as the reprojection error on the validation images shows us. I mentioned earlier that the errors that we see here are average errors. But I'm more interested in the maximum error. I want to know the worst case. So this dotted line shows the largest distance between the actual measured image coordinates and the image coordinates predicted by our model. Clearly it's a lot larger than the average, about 2 pixels. Considering that I'm using a sensor of 6000 by 4000 pixels, a maximum error of 2 pixels isn't too bad. But of course, we want to know how these errors are distributed. So this is a plot of all points extracted from the validation images, and the colors show the error. And clearly, the error is largest towards the corners. Depending on your application, after the distortion correction, you may crop your image to only keep those parts that don't contain any black pixels. So you may lose some parts of the corners with the worst errors. Okay, let's go back to the previous plot and think about how many pictures we should take in our calibration process. And I'm afraid I can't give you an easy answer. I can't tell you, take 20 pictures. How many pictures you'll need depends on a few things, such as the quality of your pictures and the number of parameters that you need to optimize. For example, if you use a calibration target with more points, then you need to find the positions of more points, which may require more information, more images. So I'm going to talk about how I would approach the calibration. I'm not saying that this is the best way or the only way to get a good calibration, but that's what has worked well for me. First, I would take a set of validation images that you will use to judge the quality of your calibration. I took somewhere between 25 and 50 validation images in my tests. That may sound like a lot, but I think if I put the effort into calibrating my camera, then I want to make sure that I end up with a good calibration, and a larger validation set will lead to more accurate evaluation of our calibration. And as I take the pictures of the calibration data, I'd plot the spread of the points on validation images, so I can be sure that I cover the whole image, including the edges and corners. Then I'd start taking the pictures for the calibration. And as I add more pictures, I'd redo the calibration and keep an eye on how the camera parameters and the errors behave. I'd stop if the errors are low and if it looks like the parameters have stabilized, so if they don't vary much. Okay, before we finish, I just want to show an example of the output if we don't focus on taking pictures in the corners. I took fewer pictures here, so the line is a bit shorter. There are a few differences. The first is that the maximum error is larger, which you can also see on this plot. So on the left is the dataset with few target points in the corners, and on the right is the dataset that we used before. The second thing that I'd point out is that the location of one of the principal points is off, and that's probably because we're missing the constraints imposed by the points in the corners. Let me also show you what the result would look like if we didn't optimize with the release object method, but with the standard method. So with the method that assumes that we know the locations of the target points exactly. This is computed on the same dataset as before, but the result is way worse. One more thing is that the release object method gives an estimate of the actual coordinates of the target points. For example, this is what it estimated for the piece of paper that I used in this calibration. And clearly, this is not perfectly flat, so it makes sense that the default method won't give a good result. Okay, that's all I wanted to say about calibrating your camera with OpenCV. If you think this video has helped you, then do give it a like and tell your friends and colleagues. The next video will probably be about another topic in computer vision. And if you don't want to miss it, then consider subscribing. So thanks for watching and see you soon.